Hello, welcome to the third part of the Cellular Automata series in TouchDesigner. In this video we will be looking at how to make a two-dimensional cellular automata. In particular, we will be creating the Game of Life by John Conway. Before we dive into it, let's look at the principles. So we saw that with a one-dimensional cellular automata system, we had something like this, where we're checking the left, the right neighbors and the state of the current cell to come up with some possible states and some rules that will determine whether the cell will be alive or dead in the next generation. If we take a similar strategy with the two-dimensional system, we come up with something like this, where we have the current cell represented by this me, and we need to check at the left and right neighbors, but also the up and down neighbors and the diagonals. So by doing this, we come up with a table that looks a little bit like this. So we have the states. This is an arbitrary state that I have chosen. And if we do all the process of calculating how many permutations there is for this and how many rules we can come up with, then we end up with a number that looks like this. That is a humongous number and really unfeasible for us. And I don't even want to encourage you to do it by hand, not even the first 10 ones. So let's not do this. That's way too unpractical. We're going to take a different strategy. Our strategy is going to be a much simpler one, which is as follows. We check the current cell. In this case, my current cell is alive. And we also check how many neighbors it has. And we count the neighbors, including the cell itself. So for example, this cell here is alive and has 4 living neighbors because I'm including itself. So 1, 2, 3, and 4. And we do this to simplify the neighbors checking. And this is called a outer totalistic cellular automata. That is when the state of the cell at time t depends on its own state and the total sum of its neighbors. So the Game of Life operates exactly like this. I encourage you to research a little bit about it, read some information online. You can check the Wikipedia page, has a lot of useful information. And they come back to the video to check further once you read some of the available information. What we care about more or less to proceed is the rule set, which is defined here. So any live cell with fewer than 2 live neighbors dies as if under population. Any live cell with 2 or 3 live neighbors lives on to the next generation, and so on. All these rules can be further simplified to just this. Any live cell with 2 or 3 live neighbors survives, and any dead cell with 3 live neighbors becomes a live cell. So keep in mind that it's quite important to check whether the current cell is alive or dead, and as well the amount of neighbors it has. So it's not the same for a living or a dead cell. And that is pretty much what we're going to be implementing now using our shader. Okay, so let's dive right into it. Let's begin by creating a base. Our base is going to be called Game of Life. In here, let's create a shader, GLSL, and let's begin to write some code. We will be creating this from scratch, so we are not going to adapt what we did before, because I think it's more clear if we do it from the beginning. Okay, let's think about it for a second. We still need to have some cell, so we're gonna still do a struct cell that is gonna be in some position, and it's gonna have a state for alive or dead. So that will be my cell. The only thing that changed now is that we have 2 dimensions, and the way we check the neighbors is a bit different. So let's see. First of all, we need some cell. We're gonna call this cell C. The position is gonna be initialized to something, and that has to be the position of the pixel in the grid. So to do this easily, let's just choose an iVec2 XY, which is gonna be simply the iVec2 version of the coordinates xy, because it's easier to think about it in this integer way and not in a normalized way. And let's just pass that to our cell. And for the alive state, we need to initialize it to the grid itself in t-1. So to do that, we need to sample the grid. So we need a text cell fetch std to the inputs, and here we need to grab the data, so the grid itself. Let's define data to be 0, so the first input of the shader, and in here we need the current position, the pixel, 0 for level of detail, and we just need the R channel, and we cast this to an int because alive is an int. Perfect. We have an error now because the std to the inputs is not defined, since we don't have anything here. So let's do what we did before. Let's put here an out, and let's simply do a feedback loop in here, like that. And feedback doesn't like not to have anything there, so just make some constant with some color, black or whatever. Well, the color doesn't really matter, we're not going to use this. And there we have it, our feedback loop is going. Perfect. So this is going to be taking the state of the grids of all the cells in t-1. Because yeah, the feedback delays with 1 frame whatever comes out of here, so that's great. Now, what we need is to initialize the alive state to some seed. Remember before we did that for the one-dimensional system, we chose the center pixel to be alive so that the system could grow. We need to do something similar here based on some trigger. So let's just do that like this. If a uniform that we're going to define in a second is on, then the value, the alive state is going to be equal to, well, just copy this, but not the data, but the seed. So our seed will be the second input. We're going to pass some texture here that is going to be our initial state. So let's define this here as the second input. And it's going to complain again because we don't have an input yet. And also because we didn't define our reset. So let's define first our reset. That will be an int. And now let's pass something here. What do we need to pass? What better to pass our beloved TouchDesigner banana? This will be our initial state. But first, let's fix a couple things here. We need to define our reset. Let's just say it's 1 to test it. Let's change the dimensions to be something different. So let's do 64 by 64. Or better yet, let's already define here on the top page with controls. In here we want to pass our dimensions. And we also want to pass a reset, so we're going to use a momentary button for that. Great. So our dimensions will be 64 by 64, and we have our reset. Let's make this visible. Put here the parameters. X and Y. And in here, let's also make the size of this banana to match that. So we're just gonna put here the dimensions. This should be Y. Great. And because we simply need to check between a binary values of 0 or 1, we don't need all this color representation. We can simply use a threshold to give us a 1 or a 0 from the pixel. And we're going to pass that here. Perfect. So now we have the grid, so the data, and the seed, the initial state. Perfect. Now, let's proceed. If it's not resetting, and we need to test this somehow, Let's first, before we proceed then, let's first pass this alive to the color so we can check this works. So see that alive. So that should be now a banana because my reset is on, and we want this reset to be the here, this one. All right, so that's good. Now we need to do something when the reset is not on. And now let's see what we need to do here. We need to create our logic. So processing here. And in the logic, what we really need to do is to check our neighbors. We're going to pass here the cell itself. And we're going to create now a function called check neighbors. Let's do this like before. We did a void. We simply pass an in-out cell C, so we don't need to output anything. And in here, we need to start to think about how do we sample the neighbors. All right. Now let's check the case. Let's see we're here, and we are in this pixel here. So that will be in here, right? And we need to sample all this microgrid from that pixel. So we need to create a microgrid inside this spot. So in fact, the grid will look something like this. So will be 0. So assuming we're in this pixel, 0 will be this pixel here, 1 will be this pixel down here, 2 will be that pixel there. So let's see, 0, 1, 2. The next row will be pixel 3 here. Then this pixel or the cell itself will be 4, then 5. And finally, the last row will be 6, 7, and 8. So we need to create this tiny grid. Now, how do we do that? If you notice, we could, for example, do a matrix, a 3x3 matrix. That will be one way. But perhaps we can do something simpler, and that will be, why don't we create a vec2, an array of vec2 called chords, and this has to be of size 3x3, so that's 9. And in this array, we're simply going to create the coordinates for those positions. So again, coming back to this pixel, the 0 value, so this one here, will be equal to position -1, -1, right? So we do here vec2, -1, -1. Then this pixel right here, if this is the cell, will be position 0s because 0 doesn't change, and -1 under. So we do vec2, 0, -1. And finally, this one will be +1, -1. So 1, -1. Great. So we have now this first row. Let's do the second row. Luckily, we don't need to think about it anymore because we simply need to replace one dimension. So now we're in row 1 and 2. Sorry, this will be -1. This will be 1. This will be 0, 0. Oops, this will be 1, 1. Now we have all the rows. Let's just align them so this is very clear. Because all we're changing is the x and the y is just the rows, so that's why what I did here. And now we need to sample them. What we could do is something like we did before. We defined, for example, the coordinate 0 to be something, but in this case, what we truly need, if you remember, this is a totalistic, an outer totalistic system. So we need to check the sum of all the alive neighbors and the state of the current cell. So for that purpose, we're just simply going to do a sum. And if you ever wrote, for example, a filter in GLSL, this is pretty much like writing a kernel. So int I equal to 0, I is 9, because we have 9 elements, and I plus plus. Now in here, we're gonna add the values that we encounter at each of these cells. So for that purpose, we're gonna use the texel fetch. We're gonna be sampling from the data, and the location of this cell is gonna be an I-vec2, the position of the cell itself, plus the coordinates we just counter. So to recapitulate, if I'm here and I want the first pixel, so this guy here, then I use the first index here, and we see the indexes here, 0, 1, 2. So 0, that means this plus -1, -1, which gives me here. So that's what's going on here. Chords I, and for the level of detail 0, we just need the R channel. We need to cast this to an int. There we go. That should give us the sum. Now, after this, we need to come up with the logic. And the logic was defined in our notes here. So let's revise the notes quickly to see what we need to write there. We saw the rules are like this, and we also said that we could simplify them to be this. So any live cell with 2 or 3 live neighbors survives, and any dead cell with 3 live neighbors becomes a cell. The thing to consider is that the way we're implementing this, we're taking into consideration the cell itself. So when they say here 2, for us that will be 3, and 3 for us will be 4. That is because we're counting the cell itself. So now let's check the case for when the cell, any dead cell with 3 live neighbors becomes a cell. Okay, so if the sum is equal to 3, then the value or the alive will be equal to 1. And yeah, this also will account for the first case, because the first case, the first case is 2 or 3 live neighbors survives. So that means for us 2, that's this 3. So that accounts for that case. And any dead cell with 3 layers becomes a cell. So also that accounts for that case. So okay, perfect. That is the first part. Then we check else if, the sum is equal to 4, because here we see 3, so that 3 is for us 4. The sum is equal to 4, and the value is alive, then the cell becomes alive. And for everything else, the cell is dead. Yeah, I think that covers these rules. So the first one is the case where either dead or alive, it has this amount of neighbors, so 2 neighbors. And the second case is when it has 3 neighbors and is alive, and everything else is dead. So that covers this logic here. All right. So if we have done this correctly, we should be seeing, yeah, we see some live already going on here. Great. And if we do reset, we see a banana. And from the banana, this behavior emerges. That is wonderful. So as you can see, this is it actually for the 2-dimensional system. Very, very simple, in fact. And in some way easier to implement than the 1D system, or equally easy. So now let's do a little bit of enhancements to our thing here, because I think it will be good to keep what we did before, where we had a possibility to specify the generations. So let's check that out. So let's add first here one integer generations. Here we're going to control how many generations we want to generate. Let's add also speed. And I think it would be nice to be able to click on something, maybe a pulse, to come up with the next one, next generation, if we don't want to do this automatically. So we press next, then we have a new one. Okay, let's say we want 300 generations, 30. Let's see. Now, how to do this? There's a couple of ways we could do it. I think the easiest way is to use a cache or cache top. I don't know how to pronounce that. Okay, let's use this. We're gonna put the cache after the GLSL, and I think this is the easiest and quickest. So let's just put in the cache. The size is gonna be 1. Not gonna be active all the time. Yeah, so that's the thing. And the feedback, let's do not, yeah, so nearest pixel, so we don't want any interpolation. And now we need to think about how do we want to trigger this. So basically we want that on reset, we want to sample one cache. We need to sample this when this is on. So let's create here a parameter execute. One thing we could do is actually, we could do it without the feedback loop, so just using a cache here and a select, but that creates some loop issue and it's a little bit more tricky. I don't want to focus on that too much, so that's why I'm doing it like this. So let's just do this in this way, and here is part.name. So if name is equal to reset, then what we want to do is to replace a single frame. So we use the replaces pulse from cache 1 to be able to grab that. So up cache 1.par replaces pulse, and let's just pulse that. Oops, pulse it. So if I press now reset, we have to of course set the parent here. So let's say my parent. Let's just grab all the parameters and the custom ones. And if we do reset, it should see my banana. And if I let go, the reset is already computing the next step here, but my cache blocks the flow. So that's good, because what I want to do now is to be able to press next, and next is gonna advance this replace single. So let's create another thing here. We're gonna call this put it on the pulse. So if pulse, if so name is equal to part of name, and if name is equal to next, then we're gonna do this too. Okay, so now if I do next, it grabs the next state, and I just manually can keep adding states and see how it develops in time. That's pretty neat. Super nice. And finally, let's add our counter as well, so we can do this automatically. And let's put this, let's just do exactly what we did in the previous video. So this will be speed, and then we have a counter. The counter's reset is gonna be the reset, of course, with capital R, and we clamp this from min to max. The max will be the generations. Generations, and that's it basically. The last thing is to trigger on change. So let's just do it like this. Probably there's better ways to do this, but this is what I can think of right now. So let's just do channel.name. No, what we're doing is just directly simply do this. Okay. So this is gonna trigger the cache. So if we do this, we should see automatically that the generations are going, but somehow it is still interpolated. Should be nearest pixel, and it stops when the end of the generations has occurred. So let's say we want a little bit more. So let's say 400. It will keep going until it reaches 400. So that's pretty nice. Maybe as a final step, we can do here one last thing. We can add a counter here for the current generation, so we can see where we are. And this will be simply read-only, and we're gonna set that to the current value. So let's say here current generation is equal to value, and in this way we can tell where we are in time. So that will do that. Perfect. So we have now implemented the 2D cellular system in a pretty similar fashion to what we did with the 1D version. And in the next video, we're going to represent this in a 3-dimensional setup. So it's still going to be a 2-dimensional system, but it's going to be just represented using instancing to generate the image that comes with these video tutorials. So that will be the final project for this 2D system. Hope to see you then.